Daniel Lopez is our next speaker. He graduated with honors in biomedical engineering from the Tijuana Institute of Technology in 2021. In 2022, he pursued a master's degree in digital systems at the Center for Research and Development of Digital Technology of the Instituto Politécnico Nacional, where he graduated with honors in August 2024. His thesis centered on developing hybrid classical quantum methods for computer-aided diagnosis of spine fractures in medical images. Currently, he is continuing his research as a PhD student in digital systems, with a focus on machine learning, deep learning, high-performance computing, and quantum machine learning, particularly applied to medical image diagnosis. I give the floor to Daniel Lopez.
Thank you very much for the introduction, and also thank you all for being here. I'm Daniel Lopez, like they mentioned previously, and I'm going to present here the work titled Solving the 5 Queens Problem Using Grover's Algorithm. So let's begin. I'm going to give a brief introduction of the problem, and I'm also going to give some theoretical foundations, how the problem is formulated mathematically, and then we'll see how what the approach that we took is, and then we'll look at the results and the findings that we can gather from them. So first, I'm just going to briefly explain the problem. The n-queens problem is a puzzle from 1848 formulated by Max Bessel, and it consists of placing n queens on an n by n board so that none of them attack each other, meaning that none of them are threatening each other. As we can see here, we have a 4 by 4 board on this example, and if we take a look at the positions that the queens attack, they don't threaten each other. So this is a combinatorial problem, a combinatorial optimization problem that looks to find the best solution, or the valid solution in this case. And as we can see here, if we keep increasing the size of the board, we can see that it goes and it becomes astronomical, right? So if we have a 4 by 4 board, we can see that there are around 256 possible combinations. But if then we get to a 20 by 24 board, for instance, then the amount of combinations that we have becomes astronomical, right? So there's that's one of the issues that we come into. And because of this, when we take a look at classical solvers, we see that they face exponential growth, meaning that the runtime becomes very, very large. For backtracking, for instance, a classical solver, it can maybe work well for 4 by 4 boards, but then for 8 by 8 boards, for instance, we might want to use heuristics, and so on and so forth. So because of this, we can use or consider a paradigm shift in computation. So as we've established during this presentation, we have quantum computing, right? So we can leverage these quantum computing characteristics, such as parallel evaluation through superposition, as well as interference that allow us to amplify states. And that's why we're exploring today this paradigm, this quantum computing paradigm, to solve this optimization problem. So when we go to Grover's algorithm and the speed up that it offers for this optimization problem, we see that it can reduce the time complexity from O of n to O root of n. And this algorithm, was formulated in 1996, and it consists of the following, right? So we first establish our superposition on RL qubits that represent our possible states, right? So we initialize them through Hadamard gates, and then once we put all the states in superposition, meaning that they represent all possible solutions, we then go to the oracle. And the oracle, what does is that it considers all possible constraints so that we know what solutions are valid for our problem. And once we determine these solutions and we invert the phase, then we move on to the diffuser. The diffuser amplifies these valid solutions that we want to look for, and this procedure is repeated until we get a high probability enough so that we can find these possible solutions. And once we have that, then we go to the measurement. So that's like a brief look at it, but if we try to formulate it mathematically, we can see that by defining a search space of size n, we are looking for a valid solution in this search space, right? And like we mentioned previously, Grover's algorithm allows us to reduce this time complexity to O root of n, thanks to what we mentioned, the characteristics of quantum computing, such as parallelism and amplitude amplification. So if we take a look at how the algorithm is formulated, we see that as we mentioned, we first initialize through a set of Hadamard gates. So this allows us to see all the possible solutions because the states are in superposition. Then we move to the oracle, and essentially what we want to do is to mark the valid solutions. In this case, the solution would be marked as negative, and otherwise it would be left as it is. And once we define all these solutions considering what we're looking for, then we go to the diffusion operator. So this diffusion operator, what it does is that it computes a mean of considering all possible states, and then it amplifies that amplitude considering that mean, right? If it's over or under, depending on how we're looking at things. And then from there, we keep repeating this process, right? The oracle and diffusion, so that our valid solutions are further amplified until we get a high probability enough that we can determine which solutions are valid. And as we can see here, we determine the number of solutions by considering the search space, which is represented by N, and also the valid solutions, which are represented by M. And this is the mathematical representation of applying these operations. So now, how did we formulate this problem? So what we did here is encode the chessboard first. So because we have an N by N chessboard, in this case a 5 by 5 board, we have to consider how we're going to encode these positions using qubits. So in this case, we're representing the qubits on this two-dimensional space, considering the I and J coordinates. And like we mentioned before, right, we want to look for valid solutions, marking them as a 1, and otherwise we're marking them as 0. Here we can see that we have an initial condition here. We define a queen at the top left corner so that we can leave out any a set of solutions so that the problem does not become too complex. Because if we're looking for all possible solutions, the problem would increase in complexity dramatically. So in this case, we set this queen at the top so that we can explore this, case, for instance. And we can see here that if we look at all the possible solutions, all the possible positions for queens, we can determine that there are a total of 12 qubits to represent all these possible positions, right? We're going to now look at what constraints we have to define, because we have to look for the rows, we also have to look for the columns, and the diagonals. So if we consider all these qubits, we have a total of 55 qubits, 12 for the state qubits like we mentioned, 4 for columns, 4 for rows, and then when we get to the diagonals, which are a bit more complex, we have a total of 17, including ancillas, and 18 for the oracle phase inversion, which amounts, like we said, to a total of 55 qubits. This would be what we mentioned previously, right? We're looking for the place in which the queen can be placed on, and we're going to look for 1 queen per row, 1 queen per column, and in this case, for the diagonals, we have a bit of a different equation, because the diagonals could also have no queens whatsoever. So because of this, we established that they're not equal to 1, but less than or equal to 1. So like we said first, we need to use superposition. So we use a set of Hadamard gates to set our solution states to superposition. And then for the oracle, what we do here is consider all the constraints that we mentioned previously. So we have our initial queen here, and then we're going to take a look at how the other queens line up for the rows. And as you can see here, we can formulate them as 3 variable equations that have to that all equal to 1. And we can represent this through this quantum circuit, considering all possible combinations and using 1 additional ancilla so that we can have the combination of the 3 of them, as you can see here. And the same would be done for the columns. They're also, all of them are represented through 3 variable equations, and we can also represent them through a similar circuit. However, for the diagonals, we have a special case. As we can see here, the equation is now less than 2, meaning that we can have a queen on the diagonal, but also no queens. So the circuit can be represented like this. This is a very small circuit. But we can see here, particularly here in the middle, that we have a 4 variable equation, which we'll later touch on. So that was for the other, that was from one perspective, the diagonals, but for this other, we have here that the set of equations would now go for 3, right? So these are the complex ones that we're going to take a look at briefly. but the other ones that are 2 can be represented through the same circuit. So like we said here, because we have 2 3-variable equations here, we have to consider all possible solutions, and we have additional ancillas here. And for the case for the 4 qubits, the 4 variable equation, we have a bit of a larger circuit. As you can see here, we are using now 4 ancillas so that we are able to consider all possible solutions. Some of these gates are to be able to consider all possible solutions, but they're also used to uncompute these operations, which are also important for the later stages of the algorithm. Once we've considered all constraints, now we have to check them, right? So when a solution is valid, we have to fulfill the row check, the column check, and the 2 diagonal checks. And they're all added to this another qubit that is used as a global constraint marker. And like we said during our explanation of the algorithm, we're going to invert the phase of this valid solution. So all valid solutions would have their phase inverted so that we can distinguish them from the others. And then we move on to the Grover's diffuser. However, before moving to the diffuser, we have to make sure that we reset all ancilla states. And this is, like we mentioned, because we're doing computing with other gates, we also need to clean that information. So we need to maintain the phase inversion and preserve those state qubits by resetting those state ancillas. And this is how the full algorithm looks, in which we have the superposition states, and then the oracle and the diffuser, and this is repeated k iterations. In this case, I believe it was for us around 13 iterations, I think. And just as a representation, you can see that this is the entire circuit for just 1 iteration. Here it includes all the constraints and the uncomputation, and here at the bottom we have the diffuser. So this process will be repeated several times. It's a bit of a large circuit. And the results that we got here, we can see here that we were able to determine the valid solution for this set of, with an initial queen position. And we can see that the valid solution here is marked as queen 1, queen 3, queen 8, and queen 10, I believe. And because the algorithm's process, the Grover's algorithm amplifies the amplitude of the valid solution, we can see here that the amplitude is maximized, and we see the valid solution in this case. And here's how the board would look like for a 5x5 chessboard, 5x5 problem. We can see here that this is our initial queen, and then these are the other positions that we found that do not threat the others. And we can see that in the results, when we compare not only the one that we computed, but the estimation of the execution time for later stages of this algorithm, that Grover's algorithm definitely offers speed up considerably compared to other problems, to other problem solvers that are classical, such as branch and bound, linear programming, and backtracking. And this is mostly because when we mentioned at the beginning, the time complexity and computational complexity can be considered linear for these quantum algorithms. So because of that, the execution time does not increase at all, if at minimum, right? And that's a speed up factor, like you can see here, quite considerable. And then when we talk about computational complexity, after estimating, we can also, after computing, we can also estimate how the computational complexity would look like, considering our quantum approach and the other classical approaches. And we can see here that the iterations versus repetitions ratio is very, very apparent, in which if we had 512 queens, this would be a dramatic comparison to other algorithms that have exponential complexity, for instance. And finally, so that we can look at some of the findings of this work, is that this approach allows us to optimize without evaluating all possible solutions. That's due to the initial conditions that we set and the oracle that we established. But this is important. This has to be achieved through data encoding. Optimal data encoding has to be achieved so that we minimize the use of qubits, because if not, then we're using too many ancillas, too many qubits, and that also affects computational time, and if we're using it on real hardware, it would also affect with noise and fidelity. And however, we can see here, and like we also saw in the results, that the number of iterations is reduced to the root of n, and it essentially reduces execution time and also computational complexity. And this is not only for this particular problem, meaning that it is not a static algorithm. It can also be explored in different domains. We would just have to consider the constraints and the encoding that we're doing to enhance the efficiency compared to other classical solvers. And for future work, we could also explore different combinatorial problems. In this case, there's also the n-queens completion problem, which would now consider all possible solutions without an initial condition. And we could also enhance the oracle design. Like we saw during the presentation, we had quite large circuits for some of the equations that we had, so maybe we could optimize that even further. Those are some of the references, and thank you very much for your attention.